Hello everyone, my name is Jesus Gutierrez Plascencia, and today I would like to present on the topic of thermal transport across the interface of liquid indodecane and its own vapor, a molecular dynamics study. This research has been conducted under the supervision of Dr. Z. Liang from the Mechanical Engineering Department at California State University, Fresno. I would first like to offer a quick background on the motivation behind this project, followed by a description of the methodology used in this research, such as the simulations and the working fluid model, and a summary of the results and future plans for this project. The motivation behind this project is based on the use of fuel nanodroplets in combustion. Past research has helped to suggest that cleaner and faster combustion can be achieved as the size of fuel droplets decreases. Although the thermal analysis under conventional assumptions of the evaporation times of these nanodroplets has been known to present considerable error once the diameter falls under a few tenths of microns. These discrepancies have been attributed to the presence of interfacial heat resistance, also known as a Kapita resistance, which implies that a non-negligible temperature jump at the interface is present after a heat flux is applied. This means that in order to accurately predict these evaporation times, proper boundary conditions have to be determined, such as successfully predicting the size of these temperature jumps that can no longer be ignored for systems at the nanoscale. Attempts to resolve these issues in the thermal analysis have been produced using relations based on the kinetic theory of gases to describe and predict the transfer of thermal energy through the interface based on the different transfer mechanisms driving this process. The first of these mechanisms is the transfer of heat through evaporation, where thermal energy is transferred through the interface thanks to the constant phase changes of molecules between liquid and gas states. This mechanism is described using the Schrade relation. The second mechanism is the transfer of heat through conduction, where thermal energy is transported through the interface thanks to collisions of gas molecules striking the liquid surface. And we can describe this mechanism by how frequently gas molecules strike against the liquid surface. The validation of these relations when predicting the transfer of energy has been challenging through traditional experimental methods. This has been mostly thanks to two major complications. The first one is the difficulty to obtain needed parameters such as the mass and thermal accommodation coefficients, known as the MAC and the TAC. The MAC is used to describe the probability an incident gas molecule will be accommodated to the liquid surface when striking it. The TAC is used as the efficiency of a system to transfer heat by collisions. Calculating these parameters is difficult since particles' trajectories and energy have to be tracked. The second complication is that these mechanisms can often occur simultaneously, complicating the process of determining the contribution of each individual mechanism in the heating process. So in order to tackle these issues, we make use of molecular dynamics simulations. And these simulations are a computational tool used to describe the interaction of particles using intermolecular potentials and integration of Newton's equations of motion, helping keep track of a particle's position, velocity, and force at any point in time. Making use of this advantage, the MAC and TAC can be calculated since real-time information about the atom's position and total energy can be taken at every time step. In order to obtain an accurate measurement of the MAC, incident gas molecules traveling towards the liquid surface are tracked in order to determine if they are accommodated or directly reflected from the surface. Our measurement of the MAC at different temperatures has been consistent with other published results on the topic. The measurement of the TAC requires to obtain the average energy of the incident and reflected gas particles. As seen in the figure to the right, thanks to MD, we can obtain the average energy as time progresses in order to solve for the efficiency of the energy transfer between liquid and gas molecules at the interface. Another advantage of molecular dynamic simulations is the ability to isolate the evaporation and conduction mechanisms from one another. The model system used to analyze the transfer of energy through evaporation is shown. In this simulation, two gold plates acting as a heat source and heat sink are placed at the left and right ends of the simulation box respectively. This generates the bulk movement of mass, also known as molar flux, across the central vapor region, in which a relatively constant temperature indicates that only energy is transferred through evaporation and condensation at the two liquid surfaces. In order to obtain the molar flux directly from the simulation, we make use of the sum of all molecules' velocity in the central vapor region, divided by the volume and Avogadro's number. To model the scenario in which only energy transfer occurs through conduction, the same major setup is used with the exception that the liquid slab on the heat source plate is removed. This to ensure that no evaporation occurs. The gradient in temperature across the central vapor region further demonstrates that the main transfer of energy is by conduction only. To directly obtain the interfacial heat conductance in the simulation, we simply divide the heat transfer through the system divided by the temperature jump present at the liquid-vapor interface. The working fluid used as a model fuel for these simulations is indodecane. Indodecane has been used in many other previous studies as a surrogate for diesel fuel thanks to their proximity and average chemical formulas. To drive down the computational cost of calculating a complex chain molecule such as this one, the united atom model is implemented. This model is used in order to transform the individual CH2 and CH3 submolecules across the indodecane chain into individual interaction sites referred to as pseudoatoms. With this, the simulation can ignore the individual bond interactions between carbon and hydrogen atoms. In MD simulations, the forces acting on each atom are derived from the potential energy created from the interaction with other particles in the system. These interactions are measured using 4 potential models. The first is the stretching bond between 2 adjacent pseudoatoms, analogous to the motion of a spring. Next is the bending bond formed by 3 adjacent pseudoatoms, which form an angle theta between them as described in the image. The third is a torsional bond which is obtained from 4 adjacent pseudoatoms. And finally, the Lennard-Jones potential, which states if an interaction creates a repulsive or attractive force between a pair of pseudoatoms based on the distance from each other. The results obtained from these simulations offered a favorable agreement to the results that were predicted by the kinetic theory of the gases relations. For the simulation of the evaporation mechanism, the molar flux obtained directly from MD methods is compared to the prediction of the trade relation for the evaporating and condensing surfaces. The MD result has a good agreement with both predictions, as it is close to the average molar flux experienced between both surfaces. For the conduction mechanism, both the MD result and prediction also presented a close agreement. This result is promising due to the potential the kinetic theory of gases has of predicting the temperature jump at the interface. The significance these results pose is that these relations are also able to properly predict the molar flux and interfacial heat conductance for more complex chain molecules such as indodecane, adding to their ability to properly predict these mechanisms for monatomic fluids as shown in previous studies. Building on these results, the future of the project relies on the further development and validation of these relations in more complex simulations. One of these simulations is the introduction of nitrogen gas in the vapor region in order to mimic the engine-like conditions a fuel nanodroplet would experience during combustion. This simulation is important based on past studies of argon in which the introduction of a non-condensable gas altered the results, such as decreasing the MAC for argon, and also introducing the conduction mechanism during the evaporation-only simulation. This is due to the many collisions now generated between both sets of gases in the central vapor region. Finally, the simulation of a fuel nanodroplet will also be performed. Primary trials will be performed using argon and neon as a working fluid and surrounding gas respectively. This in order to determine and troubleshoot the proper settings to run a computationally efficient simulation before spending resources on a more complex system such as indodecane. The end goal is to study the effects a curved liquid-vapor interface may present to the transfer of thermal energy between a nanodroplet and its surrounding gas. With this, I would like to thank everyone for their attention during this presentation. I would also like to thank the NSF for their support through the CBET Thermal Transport Process Program and Edison International for their support. The Extreme Science and Engineering Discovery Environment for the provision of supercomputer resources for these simulations, and the CSU LSAM Bridge to Docker program for their generous support during this time.